In the last section, we saw that the quadratic equation ax squared plus bx plus c equal to 0 has two roots normally, and you can find those roots by using the formula x equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, the part we're going to focus on for this lesson is the expression under the radical, which we'd normally call the radicand, but for this purpose we're going to call it the discriminant. So this expression here, b squared minus 4ac, is called the discriminant. And it's called the discriminant because it allows us to discriminate between certain possibilities. And because we're calling it the discriminant, very often we use a d, capital D, to symbolize it. So d is equal to b squared minus 4ac. And there are really three cases that we have to consider. We have to consider the case when the discriminant is positive, when it's 0, and when it's negative, and take a look at what the implications of that are. So let's take a look at the first case. First case is when the discriminant is positive. So, for example, let's consider the quadratic equation x squared plus x minus 1 equal to 0. What's the discriminant there? Well, the discriminant is b squared, which is 1 squared, minus 4 times 1 times negative 1. So that's 1 plus 4, because when you're subtracting a negative 4, it's like adding 4. So 1 plus 4 is 5. So we have a positive discriminant, and we can write the quadratic, or can use the quadratic formula to find the roots of this. X is equal to negative b, so that's negative 1, plus or minus the square root of b squared minus 4ac, which we just calculated, it's 5. So it's minus 1 plus or minus root 5 all over 2 times 1. And so you can see you have there two completely different roots. Root 5 is a little bit bigger than 2, so negative 1 minus root 5 is a little bit less than negative 3 over 2. And negative 1 plus root 5 is going to be a positive number. It's going to be a little bit bigger than 1 over 2, a little bit bigger than a half. So when the discriminant is positive, we say that there are two distinct, meaning different, real roots. Alright, let's take a look at the next possibility. The next possibility is that the discriminant is equal to 0. So as an example, let's take a look at x squared plus 2x plus 1 equal to 0. What's the discriminant? The discriminant is b squared, which in this case is 2 squared, minus 4 times 1 times 1. So that's 4 minus 4, which is 0. So we have a discriminant of 0. And we can use the quadratic formula to find the roots. X is equal to negative 2 plus or minus the square root of 0 all over 2. And obviously, when you add 0 or subtract 0, you're not making any change to this at all. And so this is just simply negative 2 over 2, which is negative 1. So there is really only one real root here. Now, we can say there is one distinct real root, but sometimes you will see the expression two identical real roots. And really the only purpose behind that is so that you can be consistent and say that there are always two roots to a quadratic equation. Either two real roots, two non-real roots, or two identical real roots. But for our purposes, it's perfectly fine just to say there is only one real root. Alright, now the third possibility is that, one more thing, if the discriminant is equal to 0, that means that the original trinomial, in this case x squared plus 2x plus 1, is a perfect square. So that means x squared plus 2x plus 1 is some binomial squared, and in this case it is simply x plus 1 squared. All right, let's take a look at the third case. The third case is when the discriminant is less than 0. So let's again have an example. In this case, x squared plus x plus 1 equal to 0. So what's the discriminant? The discriminant is b squared, which is, in this case, 1 squared, minus 4 times 1 times 1, so that's minus 4. So we get a discriminant of negative 3. And we can use the quadratic formula to find the discriminant, or sorry, the roots, negative b, which is negative 1, plus or minus the square root of negative 3 all over 2. And for our purposes, for high school math, we're not allowed to take the square root of negative 3. And so we can stop right here and say there are no solutions or no roots. Or more precisely, we can say there are no real roots. All right. Now, there's one more subtle distinction if the discriminant is greater than or equal to 0. So if the discriminant is greater than or equal to 0, we have to consider two possibilities. One, d is a perfect square. And the other possibility is it's not a perfect square. So d is not a perfect square. So again, let's take a look at a couple of examples. X squared plus 5x plus 6 equal to 0 leaves you with a discriminant of 5 squared minus 4 times 6, so that's 25 minus 24, which is 1, which is indeed a perfect square. And looking at that trinomial, x squared plus 5x plus 6, you know that you can factor it. X plus 2, x plus 3, so you get the roots negative 3 and negative 2. And you'll get the same thing if you use the quadratic formula. X is equal to negative 5 plus or minus the square root of 1 all over 2, which is simply negative 5 minus 1, or negative 6 over 2, or negative 5 plus 1, negative 4 over 2. And so you get the same roots that you would get if you factored, which is negative 3 and negative 2. So if d is a perfect square, the roots end up being rational. So rational roots. And it means you could factor the original trinomial. So the original trinomial can be factored. So actually, this can provide us with a test. If you look at a trinomial and you say, can you factor this? One thing you can do is just simply find the discriminant, b squared minus 4ac. If that turns out to be a perfect square, then yes, you can factor it. If it's not a perfect square, then you can give up right there and say, no, it can't be factored. Let's look at the other case here. D is not a perfect square. So as an example, x squared plus 5x plus 5. So the discriminant equals 0. So the discriminant in this case is 5 squared minus 4 times 5, or 5 squared minus 20, which is just 5. And using the quadratic formula, you can see that x is equal to negative 5 plus or minus root of the discriminant, so root 5, all over 2. And these are clearly irrational roots, because you have that radical floating around. And the original trinomial cannot be factored because you cannot find two numbers with a product of 5 and a sum of 5. So original trinomial can't be factored. Didn't leave myself enough room here. Okay, so let's take a look at some problems. And essentially, all of the problems that require you just to focus on the discriminant are to do with the number of roots or the nature of the roots. So if you get a question talking about, whether there are 2 real roots or only 1 real root or no real roots, or whether the roots are rational or irrational, you know that you can pretty much just exclusively focus on the discriminant, which might be a little faster, a little quicker than actually just using the quadratic formula to find out what the roots are. And as we will see with these three examples, we can look at a whole class of quadratic equations because we're actually trying to find a value of k in every case that makes that quadratic equation have certain characteristics. So for the first one, we are trying to find values of k that make 2x squared minus 3x plus k have two distinct real roots. So the tip off right away that this is a discriminant question is they're talking about the number of roots, two distinct real roots. So what does that mean? Well, if it has two distinct real roots, we know that it means the discriminant must be positive. So we just have to calculate the discriminant. To do that, we need to know what a, b, and c are, the three coefficients. And so looking at the original quadratic equation there, we have a is 2, b is negative 3, and c is k. So b squared minus 4ac is negative 3 squared minus 4 times 2 times k. That must be greater than 0 in order for this quadratic equation to have two distinct real roots. So we just solve this inequality for k. This is 9 minus 8k is greater than 0. I prefer to add 8k to both sides. That way I can avoid dividing by a negative, and dividing by a negative is problematic at the best of times, but with an inequality you can forget sometimes to swap the direction of the inequality. Now I can divide by positive 8, so I get 9 over 8 is greater than k. And now I can reverse the direction of this because normally we want to have k at the beginning of the statement. So we can say k is less than 9 over 8. So as long as k is anything less than 9 over 8, then this quadratic will have two distinct real roots. And you can test this by picking a value less than 9 over 8, like 1 or 0 or anything negative, and just plug it in and see if it actually does give you two distinct real roots. Or alternatively, you can plug in something that is not less than 9 over 8, like 2 or 3 or 5, and see that it doesn't give you two distinct real roots. So let's try the second one. For what values of k does kx squared plus 5x minus 3 have no real roots? So if it has no real roots, that means the discriminant must be negative. And again, we need to know what a, b, and c are to do this. A is k, b is 5, and c is negative 3. So the discriminant is b squared minus 4ac, which is 5 squared minus 4k negative 3, and that must be less than 0 in order for this quadratic to have no real roots. So this is 25. The minus and the minus give you a plus, 12k less than 0. I can subtract the 25 from both sides and divide by 12 to get k must be less than 25 over 12. So as long as k is less than 25 over 12, this quadratic will have no real roots. So one last one. For what values of k does 4x squared plus kx plus k have one distinct real root? So again, it's talking about the number of roots. You know it's a discriminant question. One distinct real root means the discriminant must be equal to 0. So what's a, b, and c? A is 4, b is k, and c is k. So we have b squared, that's k squared, minus 4ac. So 4 times 4 times k. And that has to be equal to 0. So we actually end up here with a quadratic equation in k. K squared minus 16k equals 0. And the easiest way to solve that quadratic equation is by factoring. You can take out a common factor of k, and you get k times k minus 16 equal to 0. So this means that either k is 0 or k minus 16 is 0, which means that k is 16. So you have two different possibilities. Now obviously if k is 0, both terms involving k disappear, and you just get 4x squared equal to 0. And that certainly only has one real root, which is 0 itself. And then if you plug in 16, you get 4x squared plus 16x plus 16, which is a perfect square trinomial, exactly as we predicted when we saw that if you have a discriminant of 0, you get a perfect square trinomial, and that leads to one distinct real root.